we begin our discussion of section 3.3, greatest common divisors. We start with the following definition. A common divisor of two integers a and b, which are not both 0, is an integer c such that c divides a and c divides b. The greatest common divisor is the largest common divisor of integers a and b. We denote the greatest common divisor by a comma b in parentheses. We also say that a and b are relatively prime if the greatest common divisor is equal to 1. Now, important theorem 1. Let a, b, and c be integers, and let us denote the greatest common divisor of a and b by d. Then, the greatest common divisor of a divided by d and b divided by d is 1, and the greatest common divisor of a plus cb and b is ab.
Are there no restrictions on c besides that it's an integer?
Very good question. There is no restriction on c. So, naturally, we have a restriction on a and b. A and b are not both 0, because otherwise we cannot talk about common divisor at all. But there is no restriction on c. In other words, c can be 0. If c is 0, a plus cb is a. Greatest common divisor of a and b is equal to greatest common divisor of a and b. That's fine. Let us prove theorem 1. So let a and b be integers, and let us denote the greatest common divisor of these two integers by d. Let us show that these two numbers, a divided by d and b divided by d, have no common positive divisors other than 1. Here's how we do it. Let us denote by e a positive integer that divides both this and this. Since e divides this, a divided by d is equal to ke, where k is some integer. Since e divides b over d is equal to e times some integer, by definition of divisibility. Next, let us multiply both sides here by d, done. And let us multiply both sides here by d, done. Note that according to what is written here, a is divisible by de, because a is de times an integer number. By definition of divisibility, a is divisible by de. Similarly, b is divisible by de. Conclusion, de is a common divisor of a and b. Now let us go back to sentence number 1. Remember, we denoted the greatest common divisor of a and b by d. d is the greatest common divisor. de is a common divisor. Since d is the greatest common divisor and de is a common divisor, de is lesser or equal to d. And now let us cancel out d. We get the following. E is lesser or equal to 1, but e is a positive integer. The only positive integer which is lesser or equal to 1 is 1. It's exactly what is written here. E must be 1. So Here we assumed that E is a positive integer that divides both this and this. We concluded that E is 1. So, since any positive integer that divides A divided by D and B divided by D is 1, the greatest common divisor of A divided by D and B divided by D is 1. Folks, any questions here?
So to show that E is 1, do we divide that inequality that DE is less than or equal to D? We divide it by D, which would say that E is less than or equal to 1. And since E is positive, it must be 1?
Yes.
It made sense until you said that A over D, the greatest common divisor of A over D and B over D is 1. I don't see how we make that step.
So please take a look at what is written here. Let us consider any positive integer that divides both this and this. So right now, the only information about E is the following. It's a positive integer that divides both this and this, correct? So we started from this. Eventually, we concluded that E is 1. So, in short, if E divides this and this, E is 1. Conclusion, the only positive divisor of these two numbers is 1. Since the only positive divisor of these two numbers is 1, the greatest common divisor is 1.
Okay, that makes sense.
Now, let us prove this. In words, what is written here means the following. The greatest common divisor of A and B is equal to the greatest common divisor of A plus CB and B. In order to prove this, we will show that the common divisors of A and B are exactly the same as common divisors of A plus CB and B. If we show this, this will immediately follow. So, let E be a common divisor of A and B. Let us go back to Theorem 2 from section 1.5. Theorem 2 says the following. If C divides both A and B, C divides any their integer linear combination. Of course, in our case, instead of C, we have E. So, please compare this and this. If M is equal to 1, this term becomes A. If N is equal to C, this term becomes this. So indeed, by theorem 2, since E divides both A and B, E divides A plus CB. So, if E is a common divisor of A and B, E is a common divisor of A plus CB and B. Because, according to what is written here, E divides B, and according to what is written here, E divides A plus CB. So E is a common divisor of this and this. Now, let us consider a common divisor of A plus CB and B. Let us denote it by F. Again, if this divides A plus CB and D, F divides this by theorem 2. But after the cancellation of CB, what is left is just A. Conclusion: if F is a common divisor of A plus CB and B, F is a divisor of A. Conclusion: if F is a common divisor of this and this, F divides this, so F divides B and A. And now let us put pieces together. By this sentence, if E is a common divisor of A and B, E is a common divisor of this and this. By this sentence, if F is a common divisor of this and this, F is a common divisor of A and B. Conclusion: the common divisors of A and B are exactly the same as common divisors of A plus CB and B. Therefore, the greatest common divisor of this is equal to the greatest common divisor of this. We are done. Folks, any questions here?
Could you explain one more time how you or why we get the A plus CB minus CB?
Yes. Please take a look at this. Over here, we know that F is a common divisor of this and this. So I'll replace in theorem 2 A by A plus CB and leave B without change. Replace also C by F. According to theorem 2, if C divides A and C divides B, C divides MA plus MB. So we have a perfect match. Here C divides A and C divides B. Here F, we replace C by F. F divides this and F divides this. Now, over here, instead of M, we can put any integer. Instead of N, we can put any integer. Let us replace here M by 1. In this case, MA becomes A. But remember, over here, A plus CB plays a role of A. So if we replace here M by 1 and A by A plus CB, this term becomes this. Similarly, if we replace here N by negative C, plus NB becomes negative CB. So, since by theorem 2, if C divides A and C divides B, C divides MA plus MB, here if F divides this and this, F divides this minus CB. But A plus CB minus CB is equal to A. We cancel out CB. Conclusion: if F divides A plus CB and B, F divides A. Does this answer a question?
Yeah, thank you.
Other questions?
I was wondering, why did we go from E to F? If E was the common divisor between A plus CB and B, why did we switch to F in the next sentence?
Very good question. Note that over here, we are talking about a common divisor of A and B. Over here, we are talking about a common divisor of A plus CB and B. These are different pairs. Therefore, we have to denote their common divisors by different letters.
But what about the sentence right before it? Like the sentence in between the two you're highlighting?
We have to show it. We want to prove this. This is the goal. What we do is the following. First, consider a common divisor of A and B. Let us denote it by E. Then consider a common divisor of A plus CB and B. We denote it by F.
So we're trying to show that E and F are actually the same.
No, we are trying to show that this set of all common divisors of A and B is equal to the set of all common divisors of A plus CB and B. This is what we're trying to show. And the way we show it is the following. Pick an element from this set. We prove that this is an element from this set, because if E is a common divisor of A and B, E is a common divisor of A plus CB and B. Then we pick an element from this set. Let us denote it by F. We show that this is an element from this set, because if F is a common divisor of this and this, F is a common divisor of A and B.
So you're proving that the set is exactly the same, and if the set is exactly the same, then their greatest common denominator has to be the same too. Greatest common divisor, sorry.
Yeah, so we prove that this set of all common divisors of A and B is equal to the set of all common divisors of A plus CB and B. Since these sets are equal, the greatest common divisor of this is equal to the greatest common divisor of this.
Yes, that answered my question. Thank you.
Guys, other questions?
So we're first showing that if you choose any element from the set of common divisors of A and B, we're showing that that is also a common divisor of A plus CB and B. And then,
Yes.
and then when we switch to F, we're showing that any divisor of A plus CB and B is also a divisor of A and B. So if it goes
Yes.
both ways, then the sets coincide.
Exactly. Since it goes in both ways, the sets are equal. And therefore, in particular, the greatest common divisor of these two numbers is equal to the greatest common divisor of these two numbers. Done. All right. Now, why care about these two properties? Let me show you applications of this. Please take a look at the following example. Find the greatest common divisor of 52 and 272. One way to do it is to find all positive divisors of 52. Then we find all positive divisors of 272, and then find the biggest common divisor. But this is a pretty laborious process. Instead, let us use this formula. Here is how we use it. Step 1. Let us apply the division algorithm in order to rewrite 272 as 52, which is over here, times quotient plus remainder. Next, we apply this formula. By this formula, what is written here can be rewritten as greatest common divisor of 52 and 12. In other words, if you look at this formula in simple words, if you have A plus CB comma B, CB can be cancelled. It's exactly what we do here. We cancel out this term. What is left is 12. Keep going. Let us apply the division algorithm to rewrite 52 as 12, which is over here, times quotient plus a remainder. And again, by this formula, we cancel out this term. Done. And now it's totally obvious that the greatest common divisor of 4 and 12 is 4. Therefore, the greatest common divisor of 52 and 272 is 4. Next example. Next example is pretty amazing. Let me go back to Fibonacci numbers. Let us start with these two terms, 1 and 1. Obviously, the greatest common divisor of 1 and 1 is 1. Consider these two numbers, 1 and 2. Obviously, the greatest common divisor of 1 and 2 is again 1. The greatest common divisor of 2 and 3 is 1. Of 3 and 5 is 1. Of 5 and 8 is 1, and so on. So, question is it true that if we consider any two consecutive Fibonacci numbers, their greatest common divisor is equal to 1? The answer is yes. The greatest common divisor of two consecutive Fibonacci numbers is 1. But how do we prove it? Well, here's what we do. By this formula, next term is the sum of two previous terms. By this formula, we can cancel out fn minus 1. Done. And so on. Conclusion: the greatest common divisor of these two numbers is equal to the greatest common divisor of f2, f1. But f2 is 1, f1 is 1, the greatest common divisor of 1 and 1 is 1. We are done. Next, let us show that the greatest common divisor of 2a plus 3 and a plus 2 is 1. Also, let us show that the greatest common divisor of 7a plus 2 and 10a plus 3 is also 1. Moreover, we will show it in two different ways. By the way, here a is an integer number. First, let us show this and this using the theorem above. Step 1. Observe that 2a plus 3 is a plus 1 plus a plus 2, because a plus a is 2a, 1 plus 2 is 3. Now, by the theorem above, we can cancel out a plus 2, because here we have a plus 2. After the cancellation, we get this. Keep going. A plus 2 can be rewritten as a plus 1 plus 1. Since here we have a plus 1, this a plus 1 can be cancelled. Done. And now it's totally obvious that the greatest common divisor of this is 1. Therefore, the greatest common divisor of this is 1. Similarly, let us rewrite 10a plus 3 as this, which is over here, plus the rest. The rest is 3a plus 1. Indeed, 7a plus 3a is 10a, 2 plus 1 is 3. Now, since here we have same expression as here, we cancel out this by the theorem above. Done. Next, let us rewrite this as 3a plus 1 times 2, which is over here. plus the rest. The rest is a. Since this expression is 3a plus 1 times 2, we can cancel out this. Done. And lastly, since over here we have a times 3, this term can be cancelled by the theorem above. Done. And now it's totally obvious that the greatest common divisor of a and 1 is 1. Now solution 2. Observe that 2 times this, which is over here, minus this is identically equal to 1. Indeed, if we expand parentheses here, we'll get 2a plus 4 minus 2a minus 3. It's 1. Note that this immediately implies this, and problem is solved. But of course, question is, why this immediately implies this? Well, here's why. Let us denote the greatest common divisor of these two numbers by d. Since d is the greatest common divisor, d divides this and d divides this. But since d divides both by Theorem 2 from section 1.5, d divides any their integer linear combination. What we see on the left is an integer linear combination of this and this. So if d divides a plus b and 2a plus 3, d divides the whole thing. But the left-hand side is equal to the right-hand side, which is 1. So any common divisor of these two numbers divides 1. Therefore, the greatest common divisor divides 1. Therefore, the greatest common divisor is equal to 1. Done. Similarly, in order to prove this, observe that 7 times this, which is over here, minus 10 times this, which is over here, is again equal to 1. And now, conclusion. If both this and this are divisible by d, the whole thing is divisible by d, but the whole thing is 1. So any common divisor of these two is a divisor of 1. Therefore, the greatest common divisor of these two is equal to 1. Done. Any questions?
Professor, what
Yes.
happens if their linear combination isn't equal to 1? Say it's like equal to 3.
Absolutely. If over here 3, we cannot really conclude that the greatest common divisor is 1. It could be 1, it could be 3. You see it?
Yes, thank you.
Please take a look at this. This problem was taken from International Olympiad. Prove that the fraction is irreducible for every natural number n. Solution 1. Note that 21n plus 4 can be rewritten as this, and now cancel out this term. Done. 14n plus 3 can be rewritten as this, and now cancel out this. Done. Obviously, greatest common divisor of these two numbers is 1. Therefore, greatest common divisor of these two numbers is 1, which means this fraction is irreducible. but there is even a shorter solution. Observe that this, which is over here times 2, minus this, which is over here times 3, is equal to -1. So any common divisor of these two numbers is a divisor of -1. Therefore, the greatest common divisor of these two numbers is 1. We're done. Next. We already discussed what is a linear combination of A and B. If A and B are integers, then a linear combination of A and B is a sum of the form MA plus NB, where both M and A are integers. Often I will call it a linear combination, but to be more specific, sometimes I will call it an integer linear combination. Please take a look at Theorem 2. It turns out that the greatest common divisor of integers A and B that are not both 0 is the least positive integer that is a linear combination of A and B. Well, this is one of the reasons why over here I provide solution 2. Note that 1, which is the greatest common divisor of these two numbers, is indeed a linear combination of A plus 2 and 2A plus 3. Same is here. 1 is a linear combination of these two numbers. Now proof. Let us denote by D the least positive integer that is a linear combination of A and B. Means the following. D is equal to SA plus TB, where S and T are integers. Let us show that D divides A. Here is how we do it. By the division algorithm, A can be written as D times Q plus R, where R is greater or equal to 0 and lesser than D. In order to show this, we have to prove that R is equal to 0. Here's how we do it. First, let us move this to the left. R is A minus DQ. It's over here. Next, note that D, according to this, is SA plus TB. So let us replace this D by this expression. Done. Next, let us expand parentheses. If we expand parentheses, the plus becomes minus, and then QSA, which is over here, QTB, which is over here. Here is what we do next. Let us factor out A here. Done. And let us rewrite this as plus negative QT times B. Here's why we do it. R is equal to this. Note that 1 minus QS is an integer. Negative QT is an integer. Conclusion. R is an integer linear combination of A and B. So both D and R are linear combinations of A and B. Both D and R are greater or equal to 0. but d is the least positive integer. R is lesser than d. Therefore, there is no escape. R should be equal to 0. Since R is equal to 0, D divides A. In the same manner, we prove that D divides B. Conclusion: if D is the least positive integer that is a linear combination of A and B, D divides both A and B. This means the following: D is a common divisor of A and B. But how do we show that D is the greatest common divisor of A and B? Here's how we do it. Let us denote the greatest common divisor of A and B by D prime. Let us assume to the contrary that D prime is greater than D. Well, since D prime is the greatest common divisor of A and B, D prime is a divisor of A and B. Means D prime divides both A and B. But now let us go back to what is written here. Remember, D is an integer, a linear combination of A and B. D prime divides A and B. By Theorem 2 from section 1.5, since D prime divides A and B, D prime divides any their integer linear combination. But this linear combination is equal to D. Since D prime divides the right-hand side, D prime divides the left-hand side. We got a contradiction. D prime is greater than D, and D prime divides D. Cannot be. Therefore, what is written here is false. Therefore, the greatest common divisor is lesser or equal to D. So D is actually the greatest common divisor. Folks, any questions here?
In the beginning, we said that D is the least positive linear combination. Where do we account for that in the math?
How do we use the fact that it's a least positive?
Yeah.
Over here. Compare this and this. Both D and R are linear combinations of A and B. R is lesser than D. But we just said that D is the least positive integer, which is a linear combination of A and B. R is even lesser. Conclusion: R is equal to 0. There is no escape. D is the least positive. So R cannot be positive because it's lesser than D. Since R cannot be positive, R is 0.
Yeah, I got that part. I was just wondering, so we just assume in the beginning that D is the least positive integer and work from there. So, I mean, basically my question was, we don't show that in the math, like we don't have to account for it in the math because it's just assumed that D is the least positive linear combination.
Well, here's what we do here. First, let us consider all integer linear combinations of A and B. And then in this set of integers, let us pick the least positive integer and denote it by D. This is what we do.
Okay, that makes sense. Thank you.
Next, Corollary 1, Divisor theorem. If a and b are integers, then there are integers m and n such that the greatest common divisor is ma plus nb. Corollary 1 immediately follows from Theorem 2, because Theorem 2 says that the greatest common divisor is a linear combination of a and b. It's exactly what is written here. The greatest common divisor is a linear combination of a and b. Example. The greatest common divisor of 4 and 10 is 2. Since 2 is equal to 10 minus 4 times 2, the greatest common divisor of 4 and 10 is an integer linear combination of 4 and 10. Negative 2 times 4 plus 1 times 10. By the way, there are infinitely many integers that satisfy this. Here we have one out of infinitely many possibilities. This portion will be discussed later. Right now, the only thing that we're supposed to understand is this. One more remark. Divisor theorem does not give us an algorithm of finding m and n. Here we just play with numbers and come up with this. Next, show that this equation has a solution in integer numbers. First of all, one can check that the greatest common divisor of these two numbers is 7. We apply same procedure as before. Conclusion. Since the greatest common divisor of these two numbers is 7, by corollary 1, there is a linear combination of these two numbers, which is equal to 7. Means this equation has a solution in integer numbers. By the way, again, you don't have to worry about this yet. We will discuss it later. All we need right now is just sentence number 1. Next, corollary 2. The integers a and b are relatively prime if and only if there are integers m and n such that ma plus nb is equal to 1. First of all, since this is an if and only if statement, we have to prove it in two directions. Means the following. First, we prove that if these two integers are relatively prime, there are integers m and n such that ma plus nb is equal to 1. Then we prove the opposite. If there are integers m and n such that this is equal to 1, then a and b are relatively prime. So let us do it. First, let us assume that a and b are relatively prime. Means this. Let us go back to Theorem 2. By Theorem 2, since a and b are relatively prime, their greatest common divisor, which is 1, is a linear combination of a and b. Done. Vice versa. Suppose there exist integers m and n such that this is equal to 1. By Theorem 2, it immediately follows that the greatest common divisor of a and b is 1, because indeed 1 is the least positive integer that is a linear combination of a and b. So once again, the greatest common divisor here is 1 because we know by theorem 2 that the least positive linear combination is the greatest common divisor, and know that indeed 1 is the least positive integer, cannot be smaller. So there is no escape. The greatest common divisor is 1.